So now we know a few things about the fundamental theorem of arithmetic. So maybe we should look at how we use it in various contexts. And maybe the most important context for it is us computing the least common multiple, or the LCM, of two natural numbers, and the GCD, or the greatest common divisor, of two natural numbers. So in order for us to do so, let's look at the simple example. 18, for example, is 2 to the power of 1 times 3 to the power of 2, and 75 is 3 to the power of 1 times 5 to the power of 2. All right, and actually we were told probably early in our student life that in order to compute the greatest common divisor between two natural numbers, what we do is we decompose them in prime factors, and then we take only the common prime factors to the lowest power. Okay, so when we look at 18 and 75, the only common prime factor is 3, and the lowest power between 2 and 1 is 1, so the GCD of 18 and 75 is just 3 to the power of 1. Alright, now we are also taught that the least common multiple, so the LCM between two numbers, is obtained by us looking at every single prime factor involved in the prime factor decompositions of the two numbers, and we take every single one of them exactly one time to the highest power. All right, so for example, the first one is 2. Well, 2 appears in 18, it doesn't appear in 75, so we take it one time to the power of 1 in this case, right? And then 3 appears in both numbers, so we take it once, but to the higher of the two powers, so it's 3 to the power of 2. While 5 appears in the prime factor decomposition of 75, it does not appear in the prime factor decomposition of 18, so we take it as 5 to the power of 2. Alright, so we know how to compute the GCD and the LCM of two numbers. Now this is all nice when it comes to numbers that we actually know of, but if we actually have to deal with variable names, things can be a little bit tricky to write down. Alright, so let's see if we can actually use a little trick to help us write down the GCD and the LCM. So the first problem that I see here is that some prime factors, like it is in this case 3, appear in both numbers, 18 and 75, while others don't. So 2 appears only in 18, 5 appears only in the prime factor decomposition of 75. Alright, so this is really not a big problem now, but maybe when we write things down for general numbers, it can turn out into a problem. Alright, but luckily this has an easy fix. So here's what we can do. Instead of looking at the prime factor decomposition of the numbers, we can look at them having the same prime factors by maybe writing 18 as 2 to the power of 1 times 3 to the power of 2 times 5 to the power of 0. Alright, so we all know that 5 to the power of 0 is just 1, so really we didn't change the product that we have on the right hand side here. Okay, and we can write 75 as 2 to the power of 0 times 3 to the power of 1 times 5 to the power of 2. Again, we changed nothing essentially, right, because 2 to the power of 0 is just 1. Okay, now how is this useful? Well, we kind of made 18 and 75 so that they use the same prime factors. Of course, some are just fake. 2 is really not a prime factor of 75, but in this way of writing it, it appears here to the power of 0. The same is true for 5. It's really not a prime factor of 18, but to the power of 0, it makes no difference. All right, so now if we change our little algorithm by saying, well, if I compute the GCD of 18 and 75, what I'm going to do, I'm going to take every single prime factor, 2, 3, and 5, to the lowest of the two powers, right? I'm going to say, well, 2, okay, appears here 2 the power of 1 in 18 to the power of 0 in 75. So I'm going to take it to the lowest of the two, which is to the power of 0, times 3 appears to the power of 2 here and to the power of 1 here. Take the lowest of the two to the power of 1, times 5 appears to the power of 0 in 18 to the power of 2 in 75. So we take it to the power of 0. So as you can see, all these fake prime factors of 18 and 75 show up in here, but they do not influence the result because they show up to the power of 0. Okay, so we effectively get the same GCD. Okay, how about the LCM? Well, for the LCM now, we can say, oh, I'm going to take every single factor that we get in this way of writing our numbers to the largest of the two powers. All right, so 2 appears to the power of 1 here, to the power of 0 here, so we take 2 to the power of 1. 3 appears to the power of 2 in 18, to the power of 1 in 75. We take it to the larger of the two, so we take 3 to the power of 2. All right, and 5 appears to the power of 0 in 18, to the power of 2 in 75. So we take it to the larger of the two, which is to the power of 2. All right, so again, this, let's call them fake prime factors, do not change neither the LCM nor the GCD. Okay, now we can say, okay, this is a little trick. Okay, fine, how do we use this? Well, now given two natural numbers, what we can do is we can say, well, let's write A as P1 to the power of alpha 1 times P2 to the power of alpha 2 times all the way times Pk to the power of alpha k, and B as P1 to the power of beta 1 times P2 to the power of beta 2 times all the way up to Pk to the power of beta k. So some of these powers, okay, some of these alphas, some of these betas can be 0. Remember, we did not allow powers to be 0 in the fundamental theorem of arithmetic because that would just completely destroy the uniqueness of the prime factor decomposition. Okay, but now we allow, and actually we want A and B to be written in this shape where we use the exact same prime factors, but we relax a little bit the conditions on alphas and betas by allowing some of them to be 0, just like we did with 18 and 75. All right, now using this way of writing our numbers A and B, we can simply compute the GCD of these two numbers. We say, okay, we are going to take every single one of these prime numbers to the smaller of the two powers. Okay, so we are going to say GCD of A and B is P1 to the power of minimum between alpha 1 and beta 1 times P2 to the power of minimum between alpha 2 and beta 2. Okay, times and so on all the way Pk to the power minimum between alpha k and beta k. So this is our GCD. Okay, and this is the generic way of writing GCD, just like we did in the case of 18 and 75. All right, now how about the LCM of the two numbers A and B? Well, what we did here, we took every single one of these prime numbers to the larger of the two powers. Okay, well, that's exactly what we are going to do here. So we are going to say P1 to the power of larger, which is maximum between alpha 1 and beta 1. All right, times P2 to the power of larger between, or maximum between alpha 2 and beta 2, times all the way times Pk to the power of maximum between alpha k and beta k. So now we were able to write in a very nice way expressions for GCD of two numbers A and B and LCM of the numbers A and B. All right. Now, if this is the entire benefit of actually us looking or writing down GCD and LCM like so, it would really not be that big of a deal. But if we notice a very simple equality that says the minimum between two numbers alpha and beta plus the maximum between the same two numbers is actually equal to alpha plus beta, and maybe the eager student would like to stop the video now and check this equality. All right, so if we notice this equality, then by multiplying these two numbers, the GCD of A and B and the LCM of A and B, and applying some basic formulas involving powers, we realize that GCD of A and B times LCM of A and B is just the product of the two numbers. So we actually have a very, very nice result, very important result in number theory that's used in quite a few problems intended to challenge people in contests.